Hi, for our final presentation, we decided to create a model to predict the next song in a playlist. So first, what are we trying to solve? Our group is aiming to create playlists with newly generated songs. We hope to do this by training a model to recognize patterns within playlists, and as a byproduct, be able to recommend a song based on previous tracks. The current solution to this problem is recommended playlists that Spotify has built in. In our previous research, we found that others have tried to do playlist generation, but few have tried to use deep learning techniques or to analyze the order in a playlist to predict the next song's attributes. Spotify has a built-in API function to get a track based on attributes, a function that we will be using in our project to generate songs. This is important because music is a universal way of bonding and entertainment. While dearly loved apps like Spotify and Apple Music have made music discovery a more pleasant experience, understanding the technicalities behind music recommendation and playlist curation is a fun way to better understand how exactly we're getting our music. As a group, we wanted a better understanding of how we might use deep learning to generate our own music instead of relying on the apps that we use daily. So first, the data that we used, we downloaded 103 playlists from Spotify's API, ensuring that none of the curated playlists were based upon a singular artist. The dataset included playlist IDs, track IDs, and the following attributes. The first three were based on mood, and they were danceability, valence, and energy. The second three were properties, loudness, speechiness, and instrumentalness. And the last two, context, were liveliness and acousticness. In total, the dataset included 8,025 songs, with the length of each playlist ranging from 49 to 99 songs.
So once we got that data, we wanted to see if there's any patterns that arose from like different from the different attributes to see if any of them were more predictable than other ones. And as you can see from this, there's not a whole lot that you can learn from this. It really just depends on the songs and how they work together. There is some sort of correlation, like if you see like acousticness and energy are heavily negatively correlated, and valence and danceability are heavily positively correlated. So there is some sort of patterns you can get from it, but it's not the easiest thing to look at just from exploratory data analysis. And next slide. So here's an example of what like acousticness looks like through a playlist. We wanted to get an idea of how because our whole idea of our project was based on the order of a playlist, we wanted to get an idea of how they move, how like the different attributes moved through the playlist. So as you can see for this top playlist, the acousticness really kind of stays at the bottom with small spikes in between. And then the second one is kind of just all over the place, and also in the third one, which kind of goes to show that it really depends on the playlist, and you can't really depend on a singular attribute to predict the next song. It's all about how they work together to be able to go to the next one. And it's a similar thing for energy. I mean, energy is really spiking and lowering, and maybe you could find some sort of pattern from this, but it just seems like it's all over the place. And it's what we've assumed through the rest of the exploratory data analysis that we did, was that it really just depends on all the different dimensions of the different attributes. So if we could visualize that, we'd be able to better understand it. So the model that we used was we used an LSTM model. And for that, we used since our input that we wanted was 5 songs, we had like 5 steps back for that. And within the model, the layers we had a LSTM layer of 64 nodes and then a dropout layer, dropped out 0.2, an LSTM layer with 32 nodes, and a dropout layer that dropped out 0.2. And the optimizer we used was Atom. The loss we used was mean squared error, and we ended up with 20 epochs and a batch size of 16. So for a lot of those parameters, we did change them, and it didn't have a whole lot of effect on the model. We tried more epochs, different sized LSTM layers, more dropout, less dropout, more layers. And it all seemed pretty much the same. So we ended up sticking with this, which is a relatively simple model, because it was quicker to train and just made the most sense for us. So the results that we ended up getting from this was basically it was really good at decreasing the loss for the training data. Validation data, it was stabilized, but it didn't really train that much for that, which leads us to think that it's overfit. But also because we changed so many hyperparameters to try to reduce overfitness, and it pretty much stayed the same, it leads us to believe that it was an issue with our data. And because we only trained on 100 playlists, which overall isn't a lot, we just need a bigger data set to be able to train it on to get it more accurate and be able to readjust the hyperparameters for that. And so that's just something we can implement in the future. But it did produce some good results. Like we tried to, Aiden, if you want to show the API the API stuff we did, we were able to get.
Yeah, so for example, if Noah wanted to give his username, and then so it would ping the API and look at all of his playlists. And then so, for example, if we wanted to look at songs Adrian listens to, or it's not a dad phase, because that's where we actually pulled this prediction from. You have the ability to do that. And then it'll print out the last 5 songs in the playlist, but also download it as a CSV file so that you can later run your model on it and analyze it.
And so, yeah, so from songs like Losing My Religion, which sounds like this. And Big Mouth Strikes Again, which sounds like this. So it's like very clearly like a 70s, 80s alternative rock playlist. And so from there, the song we ended up getting from a online thing that could give us a song based on the
features,
based on the parameters we got. We among the suggestions was this one, Where's My Mind by the Pixies. Yeah, so as you can see, like it was able to pick up a similar song as the ones in the playlist. Well, it wasn't perfect because it did suggest some songs that weren't. It was able to pick up a relevant song.
So some future steps for improvement that we would like to see would be to train it on, if we had a more powerful computer, to train it on the million playlist data set, which is something released by Spotify with over 1 million playlists. It would also give us more of a variety, because on only 100 playlists, there's thousands of genres of music, and in 8,000 songs, you're not going to cover all these many thousand genres of music. So it was kind of hard because we couldn't train it on as much as we like. So the model might not have been as robust, and it was a little bit overfit. And if we had more data, we could do more hypertuning of the parameters, because when we were hypertuning, not much was changing on many things that we played around with. And then we would also like to actually generate full playlists instead of a couple songs. But this would take a lot of more training, because after you get past your 5 songs, your previous, because the model trains on it makes a recommendation based off the previous 5. So once you get into only model generated song recommendations, you have to be a lot more careful with that. It's actually generating the right songs. And then we would also need to update the API commands to refresh our Spotify token, because it would time out after an hour. So when we were pulling the data from Spotify, from their API, we were only allowed to do this for an hour. And then they had 500 playlists on their public account, and we were only able to access just over 100 of them. And then, yeah, so here is all of our sources. So thank you.
Thank you.
Thank you.